thanks for the introduction. So I'm going to tell you about something called the symplectic log Calabi-Yau divisor, which is very much topological in nature, but I'll try to make connections with toric actions and torus fibrations. So hopefully this is of interest to the audience here. And I want to apologize because everything I tell you here happens in dimension 4. I just don't know how to do higher dimensions. So if you're interested, then I'm sorry about that. And everything is joint work with Tianjun Li and Shenzhen Ning. We do have an archive preprint already ready, but we're also writing down a second paper on this. So, oops. So let's just start with like the most basic example, which is CP2 with its standard toric action. So you have a moment map with moment image to be this right triangle with 3 edges. And now if you take the pre-image under this moment map of each edge, that gives you a symplectic sphere. So now if you take the pre-image of the entire boundary, that will give you 3 symplectic spheres intersecting kind of head to toe. And this whole thing, D, is actually a symplectic divisor. And if you take the total homology class of this symplectic divisor, it actually represents the Poincare ideal of the first chain class of CP2. And this is a very general phenomenon. If you take any toric action on the symplectic form manifold, you take a pre-image of the total boundary, that's called like a boundary divisor. That's going to represent the first chain class. And this is an example of something we call the symplectic log Calabi-Yau divisor. Okay, so I will just give you a formal definition of what this divisor is, and then talk about some properties and try to make connections with toric actions. All right. So by a symplectic divisor, because we're in dimension 4, codimension 2 just means it's a surface. All right. So now divisor just means it's a union of a bunch of symplectic surfaces, and we require that any 2 of them is going to intersect kind of omega orthogonally with no triple intersections. Okay, that means at every intersection point, exactly 2 components intersect. Right? And now we call a symplectic divisor to be log Calabi-Yau if its total homology class, which is the sum of the homology class of its components, it represents the Poincare ideal of the first chain class. Okay, so this is a very easy, simple definition, but actually it puts a very strong restriction on both the ambient manifold and also the combinatorics and topology of the divisor itself. Okay, so to have a log Calabi-Yau divisor inside it, the form manifold has to be either rational or elliptic root. So by rational, it means it's either CP2 blow up a few points, or it's S2 cross S2. Elliptic root just means it's a sphere bounded over a torus. Right? And also, the divisor is also very restrictive. It has to be either a cycle of spheres, so like this, each component is a symplectic sphere, like this, or it can only be a single symplectic torus. And for this talk, we will only be talking about rational manifolds. So just blow-ups of the CP2 and S2 cross S2. So let me give you another 2 examples of such divisors. Again, in CP2, if you just take one line and a conic, which is degree 2 curve, they intersect at 2 points. So the union of these 2 surfaces is also a log Calabi-Yau divisor. And you can see this divisor does not come from a toric action, because there's only one toric action on CP2, and that gives you 3 lines. So not this one. Okay. And on S2 cross S2, if you think of it as a Hertzsprung surface, and then you can take 2 fibers and 0 section and infinity section, the union of these 4 spheres again gives you a log Calabi-Yau divisor. Okay. These are some examples of this. And now we want to kind of fix the symplectic form manifold and try to think of what does like the total set of all such divisors look like. Okay, quotient by some equivalence relation. And the most natural equivalence relation we can put on is just a symplectomorphism, right? So we say 2 divisors, D and D prime, are equivalent if there exists a symplectic morphism that maps one to the other. So it identifies each component of one divisor to the corresponding component of the other divisor. Okay. Then we say these two divisors are equivalent. And now we can just think of all the divisors in the fixed symplectic rational manifold, and then quotient by this equivalence relation, we get some kind of moduli, which we call LCY, stands for log Calabi-Yau of x omega. This is the symplectic form manifold we're talking about, which is just all these divisors quotient by this relation. All right. So we call it a moduli, but we don't really put any interesting topology on it. It's just, yeah, it's really just a set of equivalence relations. So I apologize for using the word moduli. Hopefully it doesn't offend anyone who is like really into, sorry? Yeah, that's what I'm gonna talk about next. Yes. Right. So, so the good thing about this type of divisor rather than like kind of general divisor is that this set of log Calabi-Yau divisors are very rigid in the following sense, that we have something called the symplectic torus theorem, which is saying, now if you have two symplectic log Calabi-Yau divisors, D and D prime, if there exists an isometry on the second homology group of X, so here by isometry, it just means it's a group isomorphism that respects the self-intersection form on H2. So as you have, if you have such a purely algebraic map, so it doesn't have to come from any diffeomorphism or symplectic morphism, it can just be any algebraic map, such that it preserves, firstly, the symplectic class, the cohomology class of the symplectic form, and also it preserves it maps the homology class of each component of one divisor to the corresponding homology class of the other divisor. Then this algebraic map can be lifted to a symplectic morphism that maps one divisor to the other so that these two divisors are equivalent. So this is a very rigid property. It is basically saying that all the information about this geometric object is encoded in the homology classes. All right? So LC or LCY is really determined by homological information. Right? So because of this, in order to study this moduli or set of equivalence classes of divisors, we can just study the set of kind of homology classes. So we cook up a new set, which is called HLCY, that stands for homological log Calabi-Yau configurations. It's basically just a sequence of second homology classes, A1 up to AK, where two consecutive ones is going to intersect by 1. And there's no other intersections between them. And each second homology class AI is represented by some symplectic surface. Doesn't have to be a surface a priori. And the sum of AI is the Poincare deal of the first trend class. Okay, so this is really basically what you get by taking any divisor and then you take the homology classes. All right, and this should be quotient by some equivalence relation. And we prove that these two sets are actually bijective to each other. And you will notice that the right-hand side is only determined by the symplectic class, not the symplectic form. So with this kind of bijection or equivalence, this gives us a way to study these geometric divisors using homological information, and we immediately get some nice properties of these things.
Is being representable by an embedded surface the same as an Amherst surface? Is that the same as having positive area?
It's not. Right. I would hope that would be true, but it's not. Yeah, there's abstractions or constructions from like Cyber-Witten theory and stuff.
So these are embedded, right?
Sorry?
These are embedded.
These are embedded. Yeah, it's represented by embedded symplectic surfaces. For immersed ones, it's possible that you could have like negative self-intersections and now coming from toric actions? Yeah, so the one with in CP2 where you have a conic and a line, then that's not coming from toroid actions. So we get these properties by studying these homological classes. Well, firstly, it's finite. And we do have some kind of upper bound formula for the number of elements here. And we also have something called stability, which is saying, I mean, we can change the symplectic form. Say we have two symplectic forms, omega and omega prime, as long as they have the same set of symplectic sphere classes, by which I mean the second homological classes, which can be represented by symplectic spheres, then they will have the same set of log Calabi-Yau divisors. Okay. And we also gave some kind of very detailed count of the number of elements in this set of equivalence classes for each symplectic form when X is small rational manifolds, that is, blow up to 3 points, and for almost all omega for general X. And while counting, there are some interesting wall crossing phenomenon. That is saying, when you have like the big set of all symplectic classes, there are some walls that is determined by the existence of symplectic spheres. And as you go across this wall, the number of elements inside this modular space just increases or decreases by some fixed number. So these are log Calabi-Yau divisors and its properties. Now let's go back to something you might be interested in, which is toric actions. So as I've mentioned, there are examples where these divisors does not come from toric actions. So we have to, restrict to a smaller set of divisors called toric, which is defined by this quantity QD being 0, where QD is this weird quantity equal to 12 minus 3 KD minus sum of self-intersection numbers of its components. So here, KD is the number of components of this divisor. So for example, you have 3 lines, then KD is 3. Right? So if QD is 0, we define this divisor to be toric. So now you get a subset of this moduli, which we call TLCY. And it turns out that there is a bijection from this set, TLCY, to the set of toric actions up to equivalence on this same manifold. So now all these properties I've mentioned, like finiteness, upper bound, stability, everything just translates to properties of toric actions. So we immediately get these things. So for example, we get that for a fixed symplectic rational manifold, the number of toric actions is finite. And also we have some kind of upper bound for the number of toric actions. So this recovers the previous result of Yau, Liat, and Martin. But we also get some new results. So for example, the stability result translates to saying that if you have two symplectic forms and they have the same set of symplectic sphere classes, then they will have the same set of toric actions. And also we get something called the connectedness of toric cone, which is saying the toric cone, which is the region inside all symplectic classes, so that there admits at least one toric action. This region is actually connected. So these two results are something that at least I don't know how to see that from a more classical perspective. Right? So hopefully I have convinced you that this divisor perspective is like new and interesting and useful to study toric actions. And right now we're only considering a subset, the toric divisors, of more general log Calabi-Yau divisors. So the next question is, what happens for general log Calabi-Yau divisors? Is there some correspondence with some more general torus fibrations? And the answer is yes. So we can think of toric actions as, not the action, but just the moment map, which is a torus fibration. And now we can think of almost toric fibrations as generalization of this. And there's actually some relation between general log Calabi-Yau divisors and almost toric fibrations. So for people who don't know what almost toric fibration is, you can just think of it as just a convex polytope, but there are some more general singularity, which is focus singularity, and there are some kind of triangular cuts on the boundary. For our case, yes, if you embed it into the standard integral Affine structure in R2, it's going to be, yeah, it rips. So that's why you have this cut. Yeah. And again, you have some kind of boundary. And if you take the pre-image of this boundary, again, it's always going to be a log Calabi-Yau divisor. And what we can prove here is that this map, which goes from given any almost toric fibration, you take its boundary to be a log Calabi-Yau divisor, this map is always surjective. Okay, so given any log Calabi-Yau divisor D, we can construct some almost toric fibration so that its boundary is that divisor. And now the natural question next is, can we get some kind of bijection as for toric actions? Okay. That is, that there exists some equivalence relation on the left-hand side so that this map is not just surjective, but also bijective. If we have this, then it will give you a kind of powerful tool to understand the classification of almost toric fibrations on four manifolds, right? And that is a question I don't know, and I would like to ask the experts here. All right, so that's all for my talk, and thank you for listening.